basically what they're looking for there is where the derivative is equal to 0. And we'll find out in chapter 3 that that's an important place for a function, is where the function has a horizontal tangent line. But right now we're just going to do the math for it. And we're given some kind of, in this case, a quotient of two functions. So I'm just going to make up a problem here that's like the ones you have to do on the paper so you can see what it's like. So let's say I have x cubed over x squared minus 2x. Okay. So, where is the tangent line horizontal? So we could plot this and find out where it is, but what we're going to do is we're going to take the derivative of this. So I'm going to let the numerator be f of x and the denominator be g of x. And to use the quotient rule, we have to find the derivative of f of x, which is 3x squared, and the derivative of g of x, which is 2x minus 2. Okay, remember the derivative of x is 1. So anytime you take the derivative of something times x, a constant times x, it's just the constant. And the rest of them, you just use the power rule. Well, I mean, we are using the power rule, but it's just easier to remember that the derivative of x or y or whatever with respect to those variables is just 1. Okay. So then we use the quotient rule, which says that h prime of x is equal to f prime of x times g of x minus g prime of x times f of x, all divided by g of x quantity squared. So we'll just put those in the formula. So f prime of x is 3x squared. G of x is x squared minus 2x minus g prime of x, which is 2x minus 2, and f prime is x cubed, and we divide that by g of x squared. So we get that. Okay. And then what we're going to do is, when you have polynomials like this, you want to go ahead and simplify it. So we'll multiply at the numerator. So we'll get 3x to the 4th, this times that, minus 6x cubed. And then we have negative 2x times x cubed, so that's 2x to the 4th. And then we have negative times a negative, which is positive. So we get positive 2x cubed, all divided by x squared minus 2x squared. And then finally we combine like terms, so we'll end up with x to the 4th minus 4x cubed over x squared minus 2x squared. Okay, so that's the derivative. So that gives us the equation for the tangent line for the original problem. And where the tangent line is 0 is where the derivative is 0. And when you have a quotient, all you have to worry about is the numerator. What the denominator is telling us is that we have a vertical asymptote at the same value of x that the original function was at. Because you've got x squared minus 2x, and you've got x squared minus 2x. So these quantities are going to be 0 at the same point. So the derivative function also has a vertical asymptote at the same place. So the function is undefined at the same place. And the derivative is undefined at the same place. So what we do here is, what are the, so let's add a page here to find x values where the tangent line is horizontal set, comma, set numerator of f prime of x equal to 0. So that means I say 0 is equal to x to the fourth minus 4x cubed. I'll factor out x cubed, so I'll get x cubed times x minus 4 equals 0. I just switched the sides. So my two solutions are x equals 0 and x equals 4. So those are the two values of x where I have a horizontal tangent. So again, you take the derivative for these cases using the quotient rule. You simplify the numerator, set that equal to 0, because that's where you're trying to find out where the tangent line is 0. And if you can factor out something, I didn't try to factor this. First thing you do when you have a higher order polynomial is to see whether you can factor out x or x squared or whatever, and hopefully what you're left with is something that's easy to do at that point, which in this case it was. Okay, so that's how the problems work. Let's just double check to make sure I did this right. So we'll go to my graphing program here. And the original function was x cubed over x squared minus 2x. Okay, x cubed over x squared minus 2x. If I did this right, so we're going to have to zoom out a little bit in this direction. So you see there's a vertical asymptote at x equals 2. So that was where the denominator went to 0. And you see we have a horizontal tangent line here at x equals 0. And what that is, we'll find out in chapter 3, that's where the function reaches a maximum, a local maximum value. And then you can also see here over right there is where the function reaches, it has another horizontal tangent line, and that's at x equals 4. So we did it right. The function's undefined, and at x equals I think it might be indeterminate at 0, but that doesn't really matter. Well, maybe it does matter, but it does have a 0 tangent line there. Maybe it doesn't. Okay, so I'll show you both things, how to use the quotient rule. So you have the last problem on the second page. You'll use the quotient rule, just like we did there. Don't worry about simplifying that. Just find f, take the derivative of the numerator, the derivative of the denominator, plug it into the quotient rule, and just get an answer. Then you will want to simplify the numerator on the second two problems on this sheet. If anybody wants to continue on, the next one says find the equation of the tangent line. I'll talk about that in a few minutes when I see somebody's getting close to getting to that point. So go ahead and continue working where you were last time. So I've just plugged into, I've taken the derivatives of the numerator and the denominator, and I plugged it into the quotient rule. The question is, how far do I go in trying to simplify this, or do I try to simplify it at all? And the answer is, I'm just going to leave it that way. Okay, so don't spend a huge amount of time trying to simplify that. I might just do it for the heck of it. Let me just see what happens here. It's not much of an improvement. At least you can combine the. I guess actually you could factor out x to the negative 2/3. Let me do that. I think you can. So maybe you could go a little further. So on the first problem, when you plug in the quotient rule, you end up with this. And if you multiply out terms, you get 2x squared minus 2x minus x squared. So these can be simplified down to a single term. That, and you set the numerator equals 0, factor out x, like we just factored out x cubed. And therefore we have two values of x where the derivative is equal to 0, which is where you have the horizontal tangent lines. So if anybody has any questions about that, let me know. I'll talk to you. Hopefully you understand that one. You can do the next one. And I'm going to give you a little idea of what you do on the one following that for people who are getting to that point. So, let's see this one. So find the equation of the tangent line to the function -1/2 plus 7/5 x cubed and x equals 0. You take the derivative, which you just use the power rule, really easy. Plug in x equals 0, which actually is going to give you a 0 slope. That wasn't the best problem picking one, but that's because if you look at the derivative, there's no constant term. So when you evaluate it, so let's actually, I don't know how far people have gotten. Hopefully, they haven't gotten too far. Let's do a different value of x. Sorry for anybody who's gotten that far. It was too easy to start with. So let's do it at x equals 1. So we at least can evaluate stuff here. So do it at x equals 1. I need to fix that in my handout. That way we'll get a non-zero slope. So you evaluate the derivative at x equals 1 to find the slope of the tangent line. Then you plug x equals 1 into here to get the corresponding y value. And then you use the known slope of the tangent line and the point on the curve to find the equation for the tangent line. That's the basic idea. So I'm going to go ahead and work the one before that. I don't know. I think I saw some people with this answer, so it must be right. Take the derivative of the numerator and the denominator, plug it into the quotient rule equation. So here's the derivatives. Here's the functions: numerator, denominator, derivative, derivative. Plug that into the quotient rule. Multiply everything out. Combine like terms. Set the numerator equal to 0. Multiply everything by -1 so that you get in the form you're familiar with. Factor it, and you get that answer. Anybody have any questions about that one? So you're going to do the last, have you done this one yet? Yeah, okay. You just need to solve for y. So just multiply out and do the fraction stuff. Yeah, the last problem, what you're going to do, there's two ways of doing it. One is to combine the two terms in the parentheses into a single fraction, and then multiply 4x squared times the numerator, and that becomes your new numerator. You could multiply it out and get x to the fourth minus 2x to the fourth over x plus 1, and then take the derivative of each one of those terms. The first one would just be a polynomial, and the second one would be using the quotient rule. So either way is okay. You can combine the fractions and then take the derivative, or you can multiply out and take the derivative of the two terms to the left. And if you combine everything, if you got to the end and simplified everything, then you'd the same answer. You don't have to do it. What you guys got? Lexi, did you do it? You didn't get that? Did anybody get that? Okay, so was it the fraction part? So the derivative of this function, this is 0, and then you get 3 times 7, which is 21. So you get 21 fifths x squared. You plug in x equals 1 into the derivative equation, you get the slope of the tangent line is 21 fifths, that thing. And then if you plug x equals 1 into the function, you get negative 1/2 plus 7 fifths times 1 cubed, which is just negative 1 plus 7 fifths, which is 14 tenths. So negative 5 tenths plus 14 tenths is 9 tenths. Those are your slope, and that's your y coordinate. X equals 1 is your x coordinate. So you stick those in to your point slope form of the linear equation. And then you multiply out the right-hand side. 1 times 21 fifths, and negative 1 times 21 fifths is negative 21 fifths, which is 42 tenths. So you get negative 42 tenths, and then you add 9 tenths, because you're moving that to the other side. So negative 42 plus 9 is negative 33. So that's how that all works out. Hopefully you saw where you went wrong. As I said, you guys might have been working on the previous problem, but there's 2 ways to solve this last problem, and I'm not going to tell you which way to do it, but you could, I'll show you the 2 different ways to set it up before you take the derivative. So this is your original equation. So you could say it's x to the 4th minus 2x to the 4th over x plus 1. And this one you'd use the power rule to take the derivative, and this one you use the quotient rule. The other option is to combine the 2 fractions here. So you'd end up with x plus 1 over x plus 1 minus 2 over x plus 1. So I've just changed that to get the same denominator. And if you combine these 2, you're going to get x plus 1 minus 2. So that'll be x minus 1 in the numerator. 1 minus 2 is negative 1 over x plus 1. And then you can multiply that out, and you'd get x to the 5th minus x to the 4th over x plus 1. So there you've got, you can use the quotient rule there on one term, or you can use the power rule on the first part and the quotient rule on the second part. Okay. think that's the answer. In this case, because it's just polynomials, we can go ahead and simplify the numerator. So I FOILed out that product to get that. That one was easy. Just multiply by 1. So this -4 plus 5 minus 1, the x to the fourths disappear. And you had 1 of those and 5 of those, that's 6, x to the 5th. And you had 1 -4x cubed. Okay. So that's it for the handout. You can turn that in.
For the quotient rule, would you add or subtract for the numerator?
Oh, you're right. Thank you. That should have been subtracted. So there, it doesn't quite get that. That was just to see if you're listening. Haha. Not really. Okay, so that, it doesn't cancel out. I was wondering about that. I was surprised that it canceled out. That's one of those cases where I should have realized it. Okay, so we get 4x to the 5th, negative, what is it, -5. So it's plus 2x to the 4th minus 4x cubed. Is that right? Yeah, sorry about that. Yes, it should have subtracted.
Can you work it? Do you get the same answer if you work it the other way?
Yeah, but you'd have to combine the two fractions together because you'd have, or combine the two terms together, but it should come out to be the same answer. What you do is the first term, if you do it the other way, you're going to get 4x cubed here, and then when you take the derivative of this, you'll end up with x1 plus 1 squared in the denominator, so you'll have to combine this one with x plus 1 squared, but it should come out to be the same answer if you simplify it down to a single fraction. Okay, so let's, oh yeah, I'll talk about higher derivatives, okay? Product rule, quotient rule, tangent lines, trigonometry. Oh, yeah, we do have to talk about a few more things, but I'm going to go ahead and assign the homework anyway. So yeah, there's a lot of problems. We have the quotient rule. We can find the derivatives of the 4 other basic trig functions. So I'm gonna do one for you here. Actually, I'll do 2 for you. So if you want to find the derivative with respect to x of the tangent of x, what you do is you use the trig identity, which says that the tangent is the sine divided by the cosine. And so that's a quotient. So we take the numerator to be the sine of x, and the denominator is the cosine of x. So the quotient rule says we need to take the derivative of both of those terms. The derivative of the sine we found out was the cosine, and the derivative of the cosine is negative the sine. Again, those come from the limit definition. You can't derive the 4 other trig functions from the limit definition. You have to use the result of your previous work of the sine and the cosine. I tried it one time and it doesn't work. They don't actually ever say. I've never found any place that says that you can actually use the limit definition. You have to use the trig definition for tangent. So that says, and let's call, in this case, h of x is the tangent of x. So h prime of x is going to be f prime of x. I don't really need the parentheses. So I'll take that out. So you take f prime of x times g of x minus f of x times g prime of x all divided by g of x squared. Okay, so there we go. In this case, you can simplify things because the numerator is going to become cosine squared x plus sine squared x divided by cosine quantity squared x. What's sine squared plus cosine squared? From trig identities. 1, yep. So the numerator is 1. And which function is 1 over the cosine of x? Which one of our trig functions? It's either the secant or the cosecant. What's that? Cosecant. Yeah, it's the secant. Yeah, it's the one you would. One doesn't. You think cosine, cosecant, but it's secant. So, so what do we have here is 1 over cosine squared, which is really the same as secant of x squared, which is secant squared of x, and you can see that's the answer. Okay, so that's how you do, and you do the same thing for the cotangent. Cotangent is cosine over sine, and so it's not surprising the numerator would again be 1, and the denominator would be sine squared, which would be cosecant squared. You get a negative sign here because of just the way the signs are relative to these derivatives. And then let's pick secant. Secant's a little bit more interesting. So if we want to find the derivative with respect to x of the secant of x, again, we know the derivative of the sine and the cosine, so we rewrite the secant as 1 over the cosine. So in this case, f of x equals 1, and g of x equals the cosine of x. So you don't have to have the function y equals 1 or f of x equals 1 is still a function. Okay, so then you take the derivative of 1, which is 0, and you take the derivative of the cosine, which is minus the sine. And then you plug that in. So I'm going to say h prime of x equals f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. So that gives me, this negatives cancel out, so I get the sine of x over the cosine of x. And something's wrong. Oh, cosine squared of x, there we go. So that's squared. But then you can say sine of x divided by cosine of x times 1 over cosine of x. So what I've done is I've just broken this squared into 2 parts, grouped one of them with the sine of x, because that's the tangent, and 1 over the cosine is the secant. So this becomes tangent times secant. So this is where your trig identities start to kick in. So this is tangent x times secant x. And you see that's the answer over there. Secant, tangent, or tangent, secant, same thing. So that's, and you do the same thing from the cosecant. You make that 1 over the sine, you use the quotient rule. So the quotient rule has allowed us not only to do just quotients, but it's been able to allow us to now have the derivatives of all 6 trig functions. Again, the derivative is the slope of the tangent line to the curve. Okay, so that's it, deriving trig functions. The last subject here is higher order derivatives. So what we've done so far is we've just done what we would call the first derivative. But if you take the derivative of the derivative, that would be called the second derivative. If you take the derivative of the derivative of the derivative, then that's the third derivative. So you can keep taking derivatives until you get to 0, or you get tired of doing them. So if my function, let's say y equals x to the fourth, or f of x equals x to the fourth, we'd say our first derivative is what we've been doing, and that's what we're mostly going to be dealing with in this class. But in physics, the second derivative is the acceleration. The first derivative is the velocity of the displacement function. So the first derivative is f prime of x, or y prime, which is going to be 4x cubed. So we just use the power. The second derivative of the original function is the derivative of the derivative. So what we do is we use 2 primes to show the second derivative. So it's f double prime of x is equal to y double prime, which is then we just take the derivative of that, which is 12x squared. And then you can take the third derivative. That's f triple prime, which is y triple prime, which is 24x. And we can take the fourth derivative. And you put use a little Roman numerals, it's like IV instead of 4 primes. And that's y to the IV, and that is going to be 24. And ultimately, with polynomials, you run out, you get to the point where you go to 0, and after that point, the derivatives are 0. So f to the fifth derivative, we'll use a little v for that, is 0. And at that point, all the subsequent derivatives are 0. The 7th, 6th, 7th, 27 million derivative is 0. So that's what it means for a higher order derivative, just to keep taking derivatives. It just means taking the previous derivative and applying whatever appropriate rules there are. Okay, so that's it. We will have physics over in the physics lab today. So we'll move. See you there at 9:15. Is there homework due today? I know there's physics homework due, no calculus homework.